Hello everyone, I'm Hussein Boskuhi and I'm so happy to be here with the last episode of Transformer tutorial, which we implemented the Transformer architecture with Pytorch in Python, and it's my honor to finish this tutorial. I had this tutorial in my mind for a while, and I'm so happy that I'm completing this. Although there were a lot of problems, including the network issues that was as a result of the thing that was going on in Iran and other things, I'm finally completing this tutorial that I had in my mind. I hope you enjoyed this video and like it. Your support, commenting, liking this video is very important for me. It shows your support, shows that I should go on with my videos, and I appreciate that. So if you like the video, if you like the tutorial, see other videos, like them, and let me know if there's any problem in the comments, or contacting me by my email, or going to the repository, create an issue in there, and all of these things that you may know. So I hope everything is great for you. So, as we discussed in the previous video, we have implemented transformer architecture in TensorFlow, and we somehow recap what we've told about transformers. But in here, we are going to talk about transformers in Pytorch and how it is implemented. It is a very important episode because mostly in your research or other type of works that you are doing on transformers, you're using the transformers library from Hugging Face, and the implementation of Hugging Face is mostly based on Pytorch. And if you want to make any changes in the codes, you should understand what is going on in the transformer model and know what is that. For example, if you are seeing the birth implementation, if you have a good understanding of transformer in Pytorch, you know what is exactly going on in that model, and you can make your changes and run what you have in your mind without any problems. So it's a very important episode. So to just focus on what you're doing in here, I have implemented the code already, because we have talked about the details previously and what is going on exactly in there. So in this video I just want to explain why this implementation is good for transformers, although there are other approaches as well, but I try to keep this approach very simple. So let's just start by importing the libraries. We need some of important libraries like pandas, numpy, seaborn. All of these things are important, but the main thing that we need in here is torch and which is like the TensorFlow cross layers. It's like that. The layers are in there, and somehow also we have functional, which we talked about, that some of the functions are in there and we will use them. So the first thing that we are going to do is the embedding layer. If you remember our transformer in TensorFlow, when we were implementing this, we had somehow embedding, and it was just a variable with a size. There was no important thing in there. We could use embedding layer in there, like what we have in positional embedding, but we didn't because we wanted to keep that simple. But here I'm using the embedding layer in here. Also, if you can see, we are again using the vocab size and embedding the embedding size, which was exactly like this. We were using the D model, which was embedding size, and our vocab size. So it is like that, but we are calling the embedding layer of torch and so that's very simple. So I just create this. Also, the structure of implementing a new layer in Pytorch is just to inherit from nn.module class, and then implement it like what we were doing in TensorFlow. You should create a constructor called the father's constructor first, and then define your layers. And instead of having a call method, we have forward method, which you implement what should go in the forward path of your model. In the next part, we are talking about the positional embedding. I just want to say that I will compare our code with the TensorFlow because it's very important to understand that whatever library that you're using is not that much hard to convert the codes within two things, because it's very simple, and the mathematics behind the thing is very important. And actually, using different libraries is based on your preference or what you like about how you're coding. For example, the type of functions that you're using in here is I think Pytorch is easier because you do not use that much of dot in there. For example, TensorFlow dot cross dot this layer and add a lot of things that are not that much important for you, or defining a variable. I think Pytorch is more simple, but I think having a good understanding of both libraries is very important. So try to learn both together. And see the videos for example, if you are learning how to implement an LSTM, so see that in Pytorch and TensorFlow together, because having a good understanding of both of them will help you to do the best. So here we are talking about the positional embedding. If you remember the formula for positional embedding, it is very simple. In positional embedding, you are doing two types of functions. First of all the things is just dividing the position by 10,000 to the power of 2 I, and divided by this number of embedding dimension, or your model dimension. All these things are together equal. And we're talking about that, and you are using sine function for when I is even, and cosine function for when I is odd. So that's very simple. First of all, we are calling this father's or the parents constructor using this super method. Then we define our embedding dimension. And then we define positional encoding to zeros. So torch at zeros, set all the values to zeros. And now, using the function that we were talking about in here, this uses sine, cosine, and the values of the sine and cosine functions, and set the values in positional encoding, and then use on squeeze a layer. Actually, on a squeeze just and makes it somehow linear in here. So it's not something that much hard. So if I'm going to talk about the positional encoding and recap that in here, in order for the model to make sense of the sentence, it needs to know the things about each role. One of them is what does the word mean, which is the embedding that we were talking about, and another one is the position of the word in the sentence. That's very important. And positional coding is just letting us know the position of the word in the sentence. In the paper, attention is all you need. Author use the following function, which I talked about that. For the evens is this, and for the for the even values is this, sine of position divided by 10,000 to the power of 2 multiplied by I divided by embedding size. And for the odd values, it is with cosine function. Instead of I, we have I plus 1. It creates positional encoding, and that's very simple. Here, position refers to the order in the sentence, and I refers to the position along embedding vector dimension. Positional embedding will generate a matrix similar to embedding matrix. It will create a matrix of dimension sequence length x, embedding dimensions. And for each token in sentence, we will find the embedding vector, which is of dimension 1 in 512, and it is added to the corresponding positional vector, which is of dimension 1 multiplied by 512 to get 1 multiplied by 512 dimension out for each token that we have. For example, if you have a backslash of 32 and sequence length of 10, and let embedding dimension to be 512, then we will have embedding vector of dimension 32 in 10 in 512. Similarly, we will have a positional encoding of that 32 in 10 and in 512. Why these are together? Because we are talking about each token. Each token has two important information for us. One of them is the meaning of that token, and another one is a position. So actually the position matrix and the embedding should be all together talking about the same thing. So this is the positional encoding, and the forward here we have an input vector, and for the output we are just doing this. We are multiplying the x into the square root of the embedding dimension and then get the size. So why we are doing this? Why we're defining a value in here. The reason for that is what we were doing in the previous video. We were talking about imposition encoding. First, by doing this, we are make embedding relatively larger, because you know that we need to have this as kind of the size of that, and then we are adding constant embedding, because it's very important. For example, consider that we, for any reason, which is not that much, that does not happen, but it's just for making sure that in the future nothing happens. We're just adding a constant to the sequence lengths, and then we are doing the calculation for getting the values. So the register buffer you can see in here, and the PE you're seeing here is very simple. So when we are saying self.PE is what we have done in register buffer. Why you're using buffer, it's just a kind of implementation that we're using in here, because it's not that much. There's no need to keep that forever. It's kind of buffering the values in there. So yeah, that's all we need to do about positional embedding or positional encoding. The next part is multi-head attention, which is the main part of the transformers. Again, I'm going to recap the attention mechanism. So what is self-attention? Suppose we have a sentence like dog is crossing the street because it saw the kitchen. What it refers to here is easy to understand for the humans. That's a dog, but for machines it's not that very simple. The self-attention mechanism just find out the relativeness between the words in there. So as a model, the process each for self-attention allows it to look at other positions in the input sequence for clues, and it creates a vector based on the dependency of each word with the other. And how it does it is basically how the embeddings work, and also the positions in there and something like that. So the first step in calculating self-attention is to create a 3-vector from each of the encoder's input vector. Which in here this is the embedding of each word. So for each word we create a query vector, a k vector, and a value vector. Each of the vectors will be dimension 1 in 64. Also, it's very important to mention that in the previous episode that we were doing it in TensorFlow, we put all of these vectors equal to x, so they were all equal to each other. So since we have a multi-head attention, we need to create have 8 self-attention heads. They calculate their values, and then we attach all of them to reach the final attention of the sentence. Why we are using the multi-head attention is very simple, because we are doing that because using multi-head attention, we are doing is somehow parallel, and our calculation is faster than just doing matrix multiplication of large matrices. So it's more simple. So that's it all. And what you're doing in here, so Again, it's very simple. We have embeddings, number of heads we have in here, single head dimension, query, key. As you can see, all of these three matrices that are equal again in here, and there's no changes in here. So also we have self-let out, which is calculated by something like the number of heads in a single head dimension. Why we're doing that is very simple, because we are we have, if you remember how the multi-head was, let me multi-head attention. So yeah, this is the multi-head attention. If you remember that, we have different heads, and everyone is a scale dot production, and you concat them. There is a linear layer, so that's the reason we are defining a linear layer with concatenating all these things together. So that's very simple. Now let's talk about the forward path in here. So first we get the batch size and the sequence lengths, and then we have the sequence lengths query. And then we have the three matrices in here with a specific view of the size that we had, batch size, sequence length, number of heads, and single head dimension. That's very simple, because first of all, we are doing each vector has this is a single head dimension, this is sequence length, we have a batch size, and we have number of heads. That's the reason that we have 4 values in here. So we are viewing them in these spaces, and then we create a matrix for them. So the K matrix is just a linear layer. We are doing that because we can make this simple. We are using linear because it makes it very simple, and it makes it learnable in there. And then we do the transpose of all these matrices. That's very important, because in the calculation, if you remember, we needed that. So and this is exactly what we needed for each one. So this is the value that, if you remember, we were talking about. If mass is not known, what should happen in the self-attention. We talked about that in the TensorFlow episode. And now, as you can see, we have k-adjusted, which is the transpose of that value. We are doing the transpose to make sure that all the values are in the dimension that we want, but the k is the matrix that's different. We are going to have the transpose of that. Because of that, we are using -1 and -2, and then we are doing the math multiplication. If you remember, after multiplication, you should divide it by the square root of the dimension of the head that you are using. So after that, you can use a softmax in here, and then again multiply it by the v vector, and that's it all. The transpose that we're doing in here just for concatenating that we were talking about, and then we have the linear layer we were talking. So this is the concatenating that we are using. We're concatenating all of these values with batch size, sequence length, and what we are actually batching is this coarse matrix. So after transposing and make it continuous and all these things, and putting it in the dimension that we want, we can get out by doing the linear layer that we defined earlier in here. So after that, we get the output. Now let's talk about the encoder layer. Now that we defined let me transformer architecture, we can see that in here that what is exactly going on in the transformers. We are going to implement an encoder. Each encoder layer is something like this. It has a multi-head attention, add normalization. Also, we have positional encoding and input embedding that we defined the layers earlier. We have feed-forward network and add normalization. So here, what exactly is going on is like that. So let's not talk about these dropout things that we have here. We are defined dropout constantly can define it in the the constructor arguments, and get that like we have done it there. But we have a feed-forward network that has 2 linear layers with a ReLU for the first one. This is exactly what we have done in the TensorFlow. It was in here. We defined two linear layers. The first one had activation function ReLU. This is here. We are defining a linear, and there's a ReLU between that, which is for the first layer, after the first layer. So, and also we have normalizations, multi-head attention, and all the things. At first, you just calculate the multi-head attention of that. You do the residual, do the dropout, and then go to the feed forward layer, and again do the residual and do the dropout for the normalization. So that's it. That's it all. It's not a very hard thing in here. This is exactly what we have done earlier. So in the encoder also we are going to use I forgot to run these cells. Let me run them first. And in the encoder part, we are just calling the encoder layer that we defined earlier with the embedding output and positional encoder. So we have embedding layer, positional encoder, embedding layer, positional encoder, and some layers of encoder layers. So we are defining the encoder, and we are we have a module list of encoder layer for I range of number of layers that we want, and it's better to say, and do the forward feed that. That's very simple. Also, we have it for decoder. It should not be transformable block. We can say that it's kind of encoder layer. I can change its name to look why it is like that, because it's somehow this thing is repeated in there, so you can say that, but I don't know what to say. I can say that transformer block in here, yes, and see here I can call that, and in here again I'm using that. So in the decoder layer, everything is very simple like it was before. We have a multi-head attention, we have layer normalization, drop out, and we have a transformer block. Why we have transformer block is basically very simple, because look, as I said, multi-head attention, mask multi-head attention, normal is add a normalization, and then you have the encoder part again repeated in here. So we are using the encoder part again in here. So that's not very hard for us. And then we have the decoder, which we are just repeating that with the word embedding and positional embedding that we had in our mind. And we are again repeating the decoder that we have in our mind. And finally, after doing this, we need to do the final part of here, which is doing the linear and softmax, which we did not do anything about the linear, but we are doing the linear with FC out, which is a linear layer, and then finally we are giving it to the softmax, and it is our output. So that's it all, and now we can create our transformer just by creating class for concatenating the encoder and encoder blocks of our thing. You can see we have a decode part, which we are calling it in here. So why we have we are doing the target mask, the word that we want to predict, and all the things, and the logics, all these things. And then forward, you are just creating the target mask. You are doing the encoding, you're calling it encoding, and you're decoding the output based on the target mask that you want to predict. So that's very simple. And this is a test of what we're doing in here. So as you can see, in our test that we are actually doing in here, we are getting the output that we wanted, that was in here before. So and this testing is for an input sequence of length of 10, a target sequence of length 10, and we're saying that we're getting it. So if you remove the number of sizes, the number of tokens that are repeated, 212, 212, and that shows that we have a sequence of 10. And finally, in this situation, we're seeing that our model is working and our code is working, but we should connect it to the real embeddings and real word embeddings, and that shows that our model is learning doing a forward pass for our transformer. So that's very simple. I think this is all about what we need to know about transformers in Pytorch. If there's any problem, you can contact me, but please learn this code very and study this code very carefully. As I said, it's very important because when you are working on Hugging Face transformers, you may face a lot of these codes in there, and understanding how it works is very important. So I hope you enjoyed this video. If you like this video, I will appreciate that, and if there's any problem, you can comment it on this video, or if there is any problem with the previous ones, you can comment on that. And thank you for supporting me, and have a nice day. Goodbye.